In this video we look at the FP2 work on trigonometric equations. The WJEC specification emphasises the fact that we need to be able to use the factor formulae to deal with things like sine of A plus or minus sine B and cos of A plus or minus cos B. We should be able to use the t equals tan half x substitution, and we need to be able to generate the general solution of trigonometric equations. So first of all, looking at the general solution of trigonometric equations, we need to be able to give the general solution of the equation sine theta equals sine alpha, or cos theta equals cos alpha, or tan theta equals tan alpha, working in either degrees or in radians. The factor formulae are the formulae given here, and fortunately these formulae are given in the WJEC formula booklet, but you do need to make sure you know where to find them. If t is tan half x, then tan x can be written as 2t over 1 minus t squared, cos x can be written as 1 minus t squared over 1 plus t squared, and sin x can be written as 2t over 1 plus t squared. The formulae for cos x and sin x are given within the formula booklet, but one thing needs to be taken care of when you're using the t equals tan half x substitution. Once you have found what you think is the complete solution, you need to go back to the original equation and investigate whether or not 180 degrees, or if you're working in radians, pi radians, is also a root of the equation. If 180 degrees isn't a root of the original equation, then the original solution that you found is correct. On the other hand, if 180 degrees is a root of the original equation, then you will need to add to your original solution the solution 180 plus k 360, or the equivalent in radians. So let's now have a look at a couple of examples. First one comes from the 2011 paper. We've got to find the general solution to the equation cos theta plus cos 3 theta plus cos 5 theta equals 0. Because we're adding a whole series of cosines together, it seems sensible to try and use the factor formulae. If we start off by using the factor formulae with cos theta plus cos 3 theta, we would obtain cos theta plus cos 3 theta is the same thing as 2 cos 2 theta cos theta. So the equation that we've got would become 2 cos 2 theta cos theta plus cos 5 theta equals 0, which really isn't very much help. We've not made it any simpler than the original equation was. If anything, it's probably more complicated than the original equation. On the other hand, if we use the factor formulae to look at cos theta plus cos 5 theta, we've got cos theta plus cos 5 theta becomes the same thing as 2 cos 3 theta cos 2 theta, which means that the equation can be written as 2 cos 3 theta cos 2 theta, that's the cos theta plus the cos 5 theta bits, plus another cos 3 theta and the bit in the middle. Now this time we've got a factor of cos 3 theta running all the way across the left hand side, so we can make some progress usefully. So we've decided we're going to write cos theta plus cos 5 theta as 2 cos 3 theta cos 2 theta. So the equation in the question becomes 2 cos 3 theta cos 2 theta plus cos 3 theta equals 0. Take the factor of cos 3 theta out of the brackets. We've got cos 3 theta times by 2 cos 2 theta plus 1 must equal 0. So either we've got cos 3 theta equals 0, or cos 2 theta equals minus a half. Now, if we've got cos 3 theta equals 0, that's the same thing as cos 3 theta equals cos 90 if we decide that we're working in degrees. If we've got cos 2 theta equals minus a half, that's the same thing as cos 2 theta is cos of 120. So now, using our general solution of equations, that means that we can say that 3 theta must be plus or minus 90 plus k360, or 2 theta is plus or minus 120 plus k360, where k is an integer. If we now look at this bit and divide through by 3, and look at this bit and divide through by 2, we obtain theta equals plus or minus 30 plus k 120, or theta equals plus or minus 60 plus k times 180, where k is still an integer. Now, the mark scheme for this question gives 2 marks for using the factor formulae to move from the original equation down to this one, then another mark for the factorisation stage, and then there are 2 marks for moving from the cos 3 theta equals 0 down to the general solution of that equation, so that's this part of the work, and another 2 marks for moving from cos 2 theta equals minus a half down to the general solution for that equation, so that's the alternative solution down here. So now let's move on to a second question, which comes from the 2012 paper. We've got to use the t equals tan half x substitution to find the general solution to the equation 3 sin x equals a tan of a half x. If t equals tan half x, then we know from the formula booklet, or even better by knowing it, that sin x is 2t over 1 plus t squared. So the equation can be rewritten as 6t over 1 plus t squared equals t. Multiplying up by 1 plus t squared gives us 6t equals t plus t cubed, which can be simplified to t cubed minus 5t equals 0, or 0 equals t times t squared minus 5. So we know that t must be 0, or the square root of 5, or negative root 5. So we've got the option that tan half x could equal 0, which is tan of 0. General solution of that is half x equals 0 plus k times 180. In other words, x equals k times 360 degrees. Alternatively, we could have tan half x equals root 5. Root 5 is the tan of 65.91. General solution of that is a half x equals 65.91 plus k 180, or x equals 131.8 plus k times 360. Or tan half x equals minus root 5, which is tan of minus 65.91, which has a general solution of a half x equals minus 65.91 plus k times 180, or x equals minus 131 plus 0.8 plus k times 360. Now, before moving on, we just need to check that 180 degrees is not a root of the original equation. If x is 180 degrees, sin x is 0, so the left-hand side of the equation is 0. But if x is 180, a half x is 90, which means tan of 90, or the right-hand side, is infinity. So we've got 0 equals infinity. Well, clearly that's not true, which means that x equals 180 degrees is not a root of the original equation. So the working that we have done so far does give us the complete general solution. The marking for this question, there are 2 marks for getting down to the stage where we've got 0 equals t times t squared minus 5, And then basically there are 2 marks for dealing with each of the 3 separate cases confidently.